So previously, we've seen that printf can be used to print strings defined in the source code. So we just use it to print constant strings like hello world. However, we often need to print formatted strings, to print the result of expressions. So this is a string where it's not fixed, so the contents of the string will change during runtime. So we'll call that a formatted string. So before we print them, we need to create them. And then we need to identify the type of variable what we're going to print using this format specifier. So in this table here, it shows the different letters what we use for representing the different types of variables. So for a signed integer, we can use D or I, for example. Unsigned integer, we can use U. Characters, C. S for string, F for floating points, and we can do hex as well. Octal. There's no binary. I still don't quite fully understand why, but we can't output binary numbers, which is quite strange when we're doing embedded systems. Often dealing with binary numbers, but there's no native way of printing out binary numbers. Like you can also print in standard or kind of exponential form as well. So we'll look at some examples now. So suppose we've got an integer. We've just called it C and we've assigned the value 85 to it. There's different ways of printing that. So if we use the U specifier, that's it. We'll start off at. So look, so this is a string here. So we define the string again in between the double quotes. So these things, so the U, this space, the equals, and this space will get printed. And then essentially when we have this % sign and then the format specifier, when that's printed to the terminal, it just gets replaced by whatever we put in here. So in this example, C has got the value 85. So it'll print U equals, the unsigned integer form of that is obviously just 85, so it'll print that. We could also, if we use %x, that'll tell it to print in hexadecimal. C is to print the character form, so that's using the ASCII. So if you look in the ASCII table, you'll find all essentially the different keys and symbols on your keyboard. Each one has then got a decimal code that represents it. So C will just print the ASCII equivalent of 85. So if you wrote that code, compiled it and executed it, this is what will be displayed in the command line. So we've got U equals 85 because that's just the unsigned equivalent of 85. And note here, we've got this /n at the end, that just tells it to start a new line, because otherwise, without that, we'd just end up with this type of thing. It'd all just be on the same, all on the same line. So we put /n to start a new line. And we've got, it'll print out x equals 55, so 55 here is just a hex equivalent, so it's, instead of writing this, you often see it like this. So this will print out 0x, and then it'll actually put the hexadecimal value there, so we'd end up with x equals 0x 5 5. So that can just make it a bit easier to see. If you include this bit first, it can just make it a bit easier to see that it's a hexadecimal value. And then C, I'll print the ASCII equivalent. So if you look in the ASCII table, you'll see the decimal value of 85 corresponds to the uppercase U. Now we're looking at this bottom box here. So I just highlighted here. There's two ways of writing this number. We can either use this exponential format ourselves. So 1 e to the minus 3. So that's just the same as writing 1 times 10 to the minus 3. Or you could actually just write. This is obviously commented out, but you could obviously just write 0.001. So both of these lines are equivalent. And then there's different ways of printing this. We can use, again, this is the same. It's going to print this string. It'll just replace, every time it sees a format specifier, it'll replace it by the value what's in that variable. Then we've got a new line at the end. So look, if we compiled and ran that, the first line would get that. So you can see if you just do %f, it prints a floating point, and it does 6 decimal places by default. But you can specify, so this is a format specifier here. You can do %, so put .4f. So that's going to tell it just to print to 4 decimal places. What we get here. If we use E, that prints it in exponential format. You can combine it, so you could do %.4e if you wanted to, and it'll do 1.0000 e to the minus 3, for example. So you can, you specify the number of decimal places as well. And G is G, the compiler will pick, depend if there's not that many decimal places, it'll print it in this form. And if it goes over a certain threshold, it prints it in this form. So G is like a standard way, letting the compiler just pick which way to print it. So we'll look at an example now. We'll start putting some of these things together. So we know about variables, we've done some operators, printing strings and so on. So we'll start to combine a few bits together now to make some code what does something fairly useful. So we know we're going to be printing, so we need to include estdio. So we'll pull that library in, so that gives us access to printf amongst other things. And then in this one we're going to use a power function. So we need to use a CMath library for this. So this is a math library, contains lots of different things, sine, cos, tan and so on. But we're going to use the pow function. And then this is another example of a preprocessor directive. So when we go to compile it, the preprocessor will run first. It'll look for any instances it finds of pi in our source code, it'll replace it by this number. So this is obviously the value of pi. So when the preprocessor runs, it'll scan through. Let's see, right, pi appears here and it appears here. So both of these will be replaced by this. So it's essentially like a text find and replace operation. So it is common practice and good practice to use uppercase. So when you use a define directive, the label should give uppercase. Makes it easy to spot in your code when it's a define and not a variable, because it's important. This is not a variable. There is not a slot in memory what stores this number. This is simply just a text replace on the source code itself. It's just going to replace these instances of pi with this value here. Then we've got our main function. So again, int main, that's defined by a curly braces, so our code is contained inside these curly braces. So first off, I'm going to create a variable called radius. So this is obviously going to store the radius of a circle. The next line, created a variable called circle area, and we're going to initialize this with the area. I'm going to calculate, obviously this is just the equation of a circle, pi r squared. So this is where we use the power function. So pow, so the radius is this, that's the part here, then that specifies the power we're going to raise it to. So you cannot do this. This, for example, in other languages, that might, you might see that symbol in other languages, but that's not supported in C++ or C. That's a bitwise XOR operation. So you need to use pow. Sometimes, for example, if you just called the radius r, for example, rather than typing that, you could just do pi times r, for example. So you need to make a kind of judgment call depending on the length of your variable name and how many, because if you're doing it to the power 8, you won't want to write r times r times r times r times r, for example. But in some cases, you might want to just do, multiply by the variable by itself, depending on the name of it. So this will calculate the area, and it'll store the results in this variable circle area. Then I'm going to create a third variable, call it sphere volume, and then we're just going to calculate the area of we're going to calculate the area of a sphere. So that's just the equivalent here. You can see I've put the brackets in here just to be sure. We're going to multiply those. That's going to be done correctly. We've got pi cubed. So we need to put power 3 here. So now this is shown, the next line shows this example of formatted strings. So we want to print a message to the terminal, radius equals %2f. So this is the format specifier. So print whatever value is here, no f, because that was a float. It's going to print it to 2 decimal places. And then the next line, you can see in this printf, because there's not, you don't have to just have one. You can print more than one variable at any one time. So here we've got 2 format specifiers. So they're both essentially the same. So print floating point numbers to 2 decimal places, and they just appear in in order. So this one matches up with this one, and that matches up with that. You could obviously have a third, of a fourth, and so on. They just match up in the same order. So if you've got however many format specifiers you've got in your string, that's how many variables you need to put here. And you can see that the variables are separated by a comma. So if you compile and run that, this is the output that'll be displayed in the terminal. So you can see because we've done 2 decimal places, we just printed that value to 2 decimal places here, and the same for these as well. So you can see it's fairly simple to do formatted strings. Now we're going to look at inputting strings, because so far I've looked at how to print strings to the terminal, but sometimes I want to read data in from the user. So we do this using scanf. So this is also part of the estdio library, just as printf. So this is kind of the input. If printf is the output, scanf is the input, and just in C++ we've seen cout is obviously the output. The equivalent of scanf in C++ is cin. But we're going to be looking at scanf just because of the memory limitations we've talked about before in microcontrollers. So estdio uses less resources than IO stream. So we're going to, since our microcontroller is further constrained in terms of resources compared to a desktop PC, we'll stick to printf and scanf. So when we want to read in data, the first thing we need to do is create a variable of the correct type to store that data, and then we can use scanf with the correct specifier to read in the data and store it in that variable. So there's some examples here. So if you want to store a char, first I've created a variable here called char. Then I've put printf command here just to print a message to the user, just tell them, please enter your username, please enter your password, please enter your PIN number. We need to give the prompt to the user. Then we can use the scanf. So because we're reading the char, we need to use this %c specifier. And then we put the name of the variable here. But note, this is very, very important, this ampersand here. We'll look later why that is, but we need to put the ampersand in front. Then there's going to be another message, then printf, it'll just print out the value that was entered just so we can check. For an integer, similar process, but now we've got an int here, change this to a %i, and again need this ampersand. We'll just print that out to the user just so they can make sure they've entered the correct number. So we use this %i. Float, the same, now we're using a float variable. So we do %f. Again, we need to put the ampersand in front. We'll see why later. And then when we print it so the user can see what they've entered, we use a %f specifier. Now when you're reading a string, a char could just store a single letter essentially. So a string is an array of letters or an array of chars, so we need to create an array. So this is what this syntax does here. So this is essentially saying we've got a series of 16 characters. So rather than having a single variable to store a single char, here we've created an array of 16 variables. So essentially we've allocated 16 slots in memory to store each letter. So for this example, we can read in 16 characters. So obviously, if you're going to read a longer or shorter string, you'd have to change this number accordingly. So again, we'll print a message to the user, telling them to enter for this instance, we'll say enter your name. And then we use a %s to tell it we're going to read in a string. Now this again is very important. So in these previous cases, you have to put the ampersand in front, because that basically tells the compiler slot in memory where to store, where that variable can be found. But with an array, we don't need to do that. If you look here, there's no ampersand here. There's no ampersand because an array actually is already pointing to an area in memory. We'll cover that later, don't worry now. But just remember, when you're reading in for like a char, an int or a float, so a single variable, you need to put the ampersand. But when you're reading into an array, using a string, you do not need the ampersand. And then we're going to print a message. We'll print this string to the user, so we need to use %s. And again, we'll just put that there. So we'll look if we run that, compiled it and ran, please enter a character. So this will just that wouldn't be there at the beginning. This string will just be printed. And then when you typed in the letter G, it would appear here. You press return, and then this line would appear again. That wouldn't be there. We'd just have this displayed. You type in 78, it would appear here. Press return, and so on. So you can see here. So when you do with a char, you can type in a single letter. But when we're using a string, we've got an array of chars, we can type in multiple letters. And then it'll print that string accordingly. So we've seen we needed to use this, what we call the address of operator, so this ampersand when reading in single variables. So basically, if you put this ampersand in front of a variable name, it tells us the memory address in which it's stored. Because the memory address, there's millions of memory addresses in the computer. Well, obviously depending on how much memory is there. Each individual slot in memory's got its own address, and this address of operator tells us which slot in memory it's stored. So by putting this in front, the compiler knows which slot that variable is stored in. So when we do scanf, it reads inputted data and it puts it in that correct slot. But we've seen when we use this array, we don't need to do that. An array already is kind of very closely related to slots in memory, essentially. So the name of the array is basically the first slot in memory where it exists. So we don't need to use ampersand when we use arrays. We need to specify the length inside the square brackets. It's very important not to exceed the bounds of the array. This is a very common cause of crashes and things. So if you allocated a certain amount of memory and then you overwrite that, you'll get you can get segmentation faults and things. It'll also be used by hackers. This is a very common thing we call buffer overflow. So if you define an array of 16 elements, for example, and you write, you can write a string longer than that. You've overflown that array, and it gives, hackers can use that to get access to memory, and then once they've got access to memory, they can start injecting code and so on. So it's important not to exceed the bounds of the array. And that's why in general it's probably better to use cin. Scanf can be a bit more insecure. So cin, if you go to any desktop, it's better to use cin, but while we're on the microcontrollers, we'll use scanf, even though it has got various limitations. So we're going to take our previous example we saw, and now we'll extend it, because before we used the fixed radius, and now we're going to let the user specify a radius. So we'll just expand our previous code. So now I've created this variable radius. I'll just initialize it to 0 again, just to be on the safe side. So we're going to print a message to the user to tell them to enter the circle radius. And now scanf to read in whatever they type on the command line. So because that's a float, we need to put %f here. And again, because it's a single variable, we need to put the ampersand in front. So we'll read in the number they type in on the command line, and we'll store it in the variable radius. We'll just print a message to them so they can check they've typed in the correct value. Then we can just do the same equations we did before and print out our value. So this now is a nice little example of a code to see. It's not too long, fairly easy. So it's an example of using variables, operators, printing strings, scanf, outputting formatting strings, and so on. So once just with this little bit of C code, you can start to do more powerful programs.